I just connected my audio. So let's wait for a few more seconds and we can get started. I hope the audio and video quality is good now. So in today's session, we'll be going through some of the linear regression based models. In the last session, we implemented all the linear regression based models using NumPy. But in today's session, we will be learning a little bit on PyTorch, and then we will implement few linear regression based models and try to understand what's happening inside. So before that, in my last session, I tried to introduce this deep learning series. So these are the things we'll be covering, right from linear regression, then logistic regression, then convolution neural network, recurrent neural networks, transformers. Then we'll be mainly focusing on libraries such as PyTorch, FastAI, and transformers. Then in the last session, we tried to cover what is deep learning, what deep learning does now, what is supervised learning, then preparing small data. So this is the one, like what we did is we tried to collect the data of both kilometers versus miles. Then we collected around 4 or 5 data sets. Then we tried to build a model to learn some pattern from it. So that's what we did in the last session. Then we try to understand what's linear model and gradient descent algorithms. And we'll be doing everything in PyTorch. So if this is our first session of this year, so maybe let me introduce a little bit on learning. So in machine learning, what learning means is, let's say you have some data set, you are trying to learn some parameters in it. So initially we try to assign all the parameters at random numbers. Then by using the results, which means label, we try to connect some patterns. So this is all about learning. So there are a few algorithms for learning. We'll be going through one by one. So generally, the main difference between supervised learning and unsupervised learning is, in supervised learning, you have the output label. Maybe let me mark. Yeah, you can see the output. But in unsupervised, there is no output. You just have the data. Then you try to learn some pattern from it. Also, if you see at the top, we said we are going to learn linear regression and logistic regression. There is a little bit confusion because both has regression on it. So let me clarify what regression mean and what's linear regression and logistic regression does. Let me write it here. So generally in machine learning, it's broadly classified into two types of tasks. There are many more, but 90 or 80% of the time, it's like regression or classification. So regression means predicting real number. For example, let's say you have some data about the house. You try to predict the price of the house. So this price of the house is like a continuous real number. It should be like this. So it's a continuous data. So this is one example. Let's say the another example is bank loan. Like how much should bank lend to someone? Loan amount. So this loan amount is like a continuous number. So we call this as a regression. Classification means you're trying to predict some classes. For example, let's say you have some house price, maybe some house data, and you are trying to predict whether this house is greater than 1 million or not. Greater than 1 million or not. This is one example. And another example is if it's yes or no or 0 or 1, we call this as binary classification. So let me give you one more binary classification example. Let's say you have some chest X-ray image or any medical images, and you are trying to say whether this is cancer or not. We usually call this as 0 or 1. So this is binary classification. And there are another classification is multi-class. So in binary classification, you usually predict 0 or 1. So it should be one, just 2. Binary is 2. In multi-class, you have more than 2 label. Let's say you got an house picture, and you are trying to predict this house is greater than 500,000 and less than 1 million and greater than 1 million or less than 500k. So these are 3 different classes. So likewise in multi-class, it can be any number of class. For example, let's say you have a dog images and the output should be any of the dog breed. So there are so many dog breeds. If we're trying to predict that, we call that as multi-class. So these are some terms. So in linear regression, you try to predict a continuous number. In logistic regression, you also try to predict a continuous number. Then you do a logistic sigmoid or any function on that. So generally, this logistic converts everything to 0 to 1 range. If it's 0 to 1 range, we can convert that as we can think that as a probability number. Then you can say if it's greater than 0.5 probability, class 1, less than 0.5 probability, maybe class 0. So that's the main difference between logistic regression and linear regression. So in linear regression, you try to predict the continuous number. In logistic regression, you try to predict number between 0 or 1. Since this is like a number between 0 or 1, we can consider this as a classification task. So now we are going to see what's generally happening in entire deep learning and machine learning models. So what's happening is you have some input data, and you have some label. We can call this as output. Then you randomly create a model. This model has some weights and biases. We'll be going through all these things in this session, but if you are a complete beginner, for your understanding, think of it like some random numbers. We are going to multiply these random numbers with the input. Then you will get the output, which is prediction. So this y hat, this is prediction or label. Sorry, not label, output. Then you can compare your prediction with real label. So we can compare label and prediction, and we can calculate the loss. So this loss tells you what's the difference between input and output. If the loss is high, means our predictions are like entirely wrong. If the loss is low, means our predictions are pretty good. So if the loss is 0, means we are accurately predicting the output as it is. If the loss is really high, means what you have to do is you have to change those random numbers a little bit here and there. Then you calculate the loss again and see if the loss decreases. If the loss decreases, means you keep on changing those weights and biases in that direction. So this changing weights and biases using some algorithm, this is called gradient descent update. So in gradient descent, what we are doing is we are randomly creating some parameters, weights and bias. Then we use those random weights and bias and we multiply that with input. Then you get some results. Then you compare the results with the original label. If the difference is huge, means you need to change those weights and biases in some direction, and you will check whether those changes reduces the loss or not. So that's the entire goal. Good. So this is how, maybe this is the good time to go through some code and we can develop. Maybe let me run this code and then we can talk about understanding more on gradient descent. Then we will implement a few PyTorch techniques. Okay. So if you are a absolute beginner and if this is your first session on deep learning, so generally for building deep learning models, we need GPUs, graphical processing unit, which does lots and lots of multiplication at once. So since in deep learning we will be doing so many multiplications, we need some GPUs. And what we are doing today is like a small dataset and toy problem. So we don't need to have a GPU, but I will, anyways, I will teach you how to choose GPUs. So this is Google Colab and this is free, but they also have few versions like Google Colab Pro and Pro Plus. Google Colab Pro is like $10 per month and Pro Plus is $50 per month, which is USD. With this, you can get some powerful GPUs. For this lesson, it's okay to have a free Google Colab. You don't need to pay anything. So first of all, what I have to do is click runtime, change runtime type. Then here you can choose GPU. GPU class, if you are like paying $10 or $50, you can choose standard and premium. Premium means they will give you like some powerful GPUs. For standard, they'll be giving basic GPUs. Both are pretty good for this lesson. No need to have any, that's fine. You can choose standard. Then let's say you are dealing with a very big file, you can choose high RAM if needed. Otherwise standard is fine. Then save. Once that's done, click connect. So currently it's creating a virtual computer based on your configuration. This looks good. Now to run, maybe let me teach you how to create some cell. If you can see it here. If you click this, it will create a cell. And if you click this one, it will create another cell, but there is a difference. This is, we call this as code. Here you can write any code, any Python code. And to execute, you can click this button, as well as you can do shift enter. And this cell is a little bit different. We call this as markdown cell. Here you can write any text, you can make it bold, you can write code, then you can attach something, image, center alignments, those kind of things. Even you can do LaTeX. So here I can type anything. To run this, shift enter. So for this session, we'll be using PyTorch and NumPy. So I'm importing Torch and checking its version. It's 1.13, I guess. Okay. Also for normal models, we'll be using like NumPy, and we are using matplotlib to visualize the results. So in the last session, what we did is we tried to collect some data set ourselves, looking it by Googling. So this is like, I think this is kilometer and this is miles. So you can see it here. Here, one kilometer is 0.62 miles. And I think this is kilometer and this is miles, I guess. Let me see that. So 1 mile is 1.60 kilometer. I think we choose kilometer here. So this should be 0.62. So one is kilometer and other one is mile. Okay. So we have collected these 4 samples. With this, we are going to build a model, and then we will ask what happens when the kilometer is maybe equal to 50, and let's say what our model says. Maybe let me do this. For 50, if our model says 31.06, then that's a good model. Maybe let me write it there. Miles equal to 31.06 or something, 0686. Okay, so we are going to develop some model, and then after developing the model, we are going to ask what's the mile for 50 kilometers. If our model says close to 31.06, then that's a good model. If it gives you like a random number, then that's totally a wrong model. Cool. So here I just plotted input data and output. Now, as I said before, we are going to initialize some random number. We are initialized 2.3. Then with 2.3, we are going to make some predictions. In deep learning and especially in PyTorch, when you're trying to make some predictions, we call this as forward. Okay. Now we are going to ask. Did I type 50? Okay. So for 50 kilometer, our model says 114 miles, which is completely wrong because this is like random. Then what we are going to do is we are going to calculate the loss. How to calculate loss is, maybe let me give you a quick refresh. Let's say, let me type this. Okay. So let's say the label is 234, and let's say the model, okay. Let's say the label is 234 and the predictions are 482. We need to find whether this prediction is really good or not. One way to find this is just subtract 2 minus 4, which is 2, and 3 minus 8, 5. I think it's y hat minus y. So which is 4 minus 2, 2, 8 minus 3, 5, 2 minus 4, minus 2. So if you see this, if I calculate the average loss, you add 2 plus 5 minus 2. 2 and minus 2 cancel each other, which is completely wrong because 2, 4 and 4, 2, there is some error in it. And if you are just adding it, it's cancelling. So one way to avoid this is take absolute difference. So if this is minus 2, change it to 2. So this is one way to calculate the loss. We call this as mean absolute error. And another way to avoid those 2 and minus 2 issue is just take square. If you take square, the negation minus becomes positive. Then 2 becomes 4, 5 becomes 25, minus 2 becomes 4. Then you add everything and then take average. We call that as mean square error. Since we squared everything, we need to take a square root. If you are going to take square root, we call this as root mean square error. Cool. So now I'm going to implement that. So our loss is mean square error. So this is mean square error. So this is not exactly mean square error. This is square error. Anyways, we'll be taking mean here. So here what we do is we give some input and output. We calculate the predictions. Then we compare the predictions with the output. Then label. Then you take square. This is square error, square loss. Good. Then what we did is we are checking different numbers. For example, initially we randomly initialized 2.3. For 2.3 we are getting some loss. Now what we are checking is what happens if we initialize some number between 0 to 2.1 every 0.1 interval and calculate the loss. So that's what I'm doing here. So I ran a few experiments. When w equal to 0 means mean square error is 2.89, and when you increase w, our loss decreases. So when you increase the weights, our loss decreases. You can see it here. So when it's 0.9, the loss is 0.58. When it's close to 0.7, the loss is 0.04. And when it's close to 0.06, the loss is very low. I think we know this. When w equal to close to 0.6, the loss is minimal. And then after that, if we increase w, the loss also increases. Now let me visualize this. So if you see this one, when weight is close to 0.6, we are getting the lowest loss. After that, if you increase, the loss also increases. Here, if you decrease weight, the loss also increases. So now we can apply gradient descent algorithm. The gradient descent will tell you which direction to go. For example, let's say our initial weight is 2. We are here. And when you apply gradient descent, it will tell you need to go this direction, downwards, here. Let's say we are starting our weight here, somewhere like 0.01. And if you apply gradient descent algorithm, it will tell you need to go this direction. So now let's get some high level intuition on how gradient descent works. If you see my right hand side, for this case, let's assume when w equal to 2, the loss is 0. And when you increase the w from 2, the loss increases. And when you decrease the w from 2, the loss increases. So for simplicity, let's assume our initial w is here. You can see it here, like when w equal to 3 or something, it's here. So the gradient descent algorithm is, you need to calculate the gradient. Gradient means slope. So how to calculate gradient is, let's say w equal to 3. You increase this w to 3.01 or something and check what happens to the gradient slope. If we increase the w, the gradient also increases. So here the gradient is positive. Okay, that's one important information. Here the gradient is positive. Let's talk about the other case. Let's say our initial w is here. What happens here is, if I increase w, the loss decreases. So this is negative gradient. Okay, so the most important thing is, here the gradient is positive, here the gradient is negative. Then with this information, we apply gradient descent algorithm. The algorithm says, to modify w, new w equal to w minus some alpha, which is learning rate, which tells you how fast you want to go down and how fast you want to change the direction. Okay, then we are calculating the gradient derivative of loss with respect to w. So this, let's say we are here, w equal to 3. W equal to 3. Here the gradient is positive. Since the gradient is positive, if you apply some positive number to w, what happens is you are subtracting. So this w becomes, it goes downhill. It goes this direction because we are subtracting. Let's say we are here in negative gradient. We need to go, let's say w equal to here means, let's say the w equal to 0.5. And we need to know, we know that when w equal to 2, that's a perfect result. But we are here now. Here the gradient is positive. Sorry, here the gradient is negative. Since the gradient is negative, you are applying the negative number here. There is already a negative here. So negative and negative, that becomes positive. So you go this direction. So that's the key understanding of gradient descent algorithms. Cool. So now we are going to implement this. So this is same data set and same forward, loss and gradient. So we know that, maybe let me write this. We know that y prediction is input data multiplied by some weight. Then we can calculate the loss. The loss is prediction minus input label whole square. So it becomes xw minus y the whole square. Then we can expand. If we expand, it becomes x square w square minus 2x wy plus y square. Then we need to take derivative of loss with respect to w. If you do that, it becomes 2x square w, then minus 2xy. There is no w term here, so it becomes 0. Then we can rearrange and we can write it here like this: 2x multiplied by xw minus y. So this is the gradient. We call this as derivative. Since this problem is super simple, we can calculate everything by hand. But generally, in deep learning, you have so many parameters, like so many layers. let's say you have some input data, you pass each data to each layer, then you get some output, then you do some transformation, then you pass that to another layer, then you pass that to another layer. In each layer you will be doing so many multiplications, then finally at the end you will get some number output. Since this network is huge, big, we cannot calculate this gradient by ourselves. For this we'll be using an algorithm called backpropagation. Backprop. So we'll be seeing backprop in the next session. But for now, to understand backprop, we are using some libraries like PyTorch or TensorFlow. So these libraries calculates all the gradient for yourself. You no need to manually compute this gradient and then put it there and calculate the derivatives. It's impossible to do that. For that, we'll be using some libraries like PyTorch. Cool. So now let's look into this. I have implemented gradient. Then now we are asking, maybe let me change this to 30 kilometer. 50. Okay. Prediction for 50 kilometer. 50. It says for 50, it says 110 miles, which is wrong. Because we haven't trained our model yet. So now we are going to train our model. So for training, what we are doing is for each data, let me introduce this epoch concept. So one epoch means passing all the input data to the models. If you pass all the data to the model once, that's called one epoch. So generally, let's say you have millions and millions of data. You cannot pass millions of data at once. So what we do is we create a batch. Let's say you have got 1,000 data points and your batch, maybe let me comment this. Okay. So let's say you have got 1,000 data points and your batch size is 100, which means at once you are passing 100 data. Now let me compute something. One epoch means passing 1,000 data to the model. Okay, which means if your model sees all those 1,000 data at once, one time, we can call that as one epoch. So let's say when batch size is equal to 100 means it needs 10 iteration of batch size 100 to complete one epoch. So these are some terms. So generally in deep learning we pass our data many times. So we call that as epoch. So here I'm doing 10 epoch. So initially our loss is 0. Then for each data we are calculating the loss. Then based on the loss we are calculating the gradient. Then we are changing those W a little bit and see what happens. So let me run this. So initially after epoch 1 the loss is 13 and our W becomes 1.41. Then after 10 epoch the loss is nearly 0. You can see e power minus 0.05, which is 0.000 something, which is very close to 0. And our W becomes 0.622. So now let's ask what happens 50 kilometer forward 50. It says 31.14, 31.06, which is pretty close. If we train our model a little bit longer, we might get even more accurate. So here what we have done to solve this problem, what we have done is the most important thing here is we calculate the gradient ourselves. And then we did gradient descent update and then we got some numbers. So now what I'm going to do is I'm going to slowly introduce PyTorch. So far we haven't used any PyTorch. Now what we are going to do is instead of calculating this gradient by yourself, let's use the power of PyTorch to calculate the gradient. And then we can change these things with the instead of gradient function, we'll be using PyTorch gradient way of doing things. Then let's see we are getting same results or not. So that's the goal. So in order to do that, I'm going to copy paste few things I have done above, and then we will change only those things so that we can type things fast. PyTorch gradient. So initially the data is same. And let's calculate forward and loss. Okay, so I have calculated forward and loss. Now the main thing is, instead of w equal to 2.2, we are going to change this to torch.tensor 2.2. And since we need to calculate gradient of w, we need to set recurse grad equal to true. Okay, so that's the change. Okay, so now let's run this. Now let's ask what happens forward of maybe 50 kilometers. It says 110. So I typed item. Before that, let's see how it looks like. Okay, since we have introduced w as tensor, since we are using tensor to do some multiplication with the numbers, our output becomes a tensor, and there is some gradient function goes there. So we'll look into this, but I just need the value. To get the value, you can just type item and you can get the value. Cool. So now what we are going to do is, we are going to remove the gradient part. So I'm not going to use gradient function. Instead of using gradient function, I'm going to use PyTorch gradient and then try to see what happens. So for epoch in range 10, for each data x comma y in zip x data y data, then we are calculating the loss x comma y. So this loss has w in it. So if you see loss, we are calculating forward. So in forward, this forward has w. Since w is like a tensor with recursive graph, it knows how to compute, how to backpropagate and then understand the gradient. So now we are calculating the loss. After calculating the loss, we are asking it to do backward. So when it's backward means it's going to calculate the gradient, L dot backward. Then once it does L dot backward, we are going to use grad function from w, grad from w, and then we are going to do gradient descent update. So I have done L dot backward. Now what I'm going to do is w dot data equal to, so if you see w, so w is a tensor. It has two things. One is data, which is 2.20, and it also has gradient, w dot grad. Currently it will throw some error message because I have not executed L dot backward yet. So let's check w dot grad. So currently it didn't show anything, which is none. Currently w dot grad is none, but when you do some backward, it changes. You will get some real number. So let's see that. So after calculating the gradient, what we need to do is we need to change this 2.2 number. So in order to do that, I'm typing w dot data equal to w dot data minus some learning rate 0.01 multiplied by w.grad. Then after this, after gradient descent update, let me type this. So after gradient descent update, we no need to compute the gradient continuously. So what we need to do is we need to set the gradient as 0. Otherwise, it will just keep on adding the gradient. We don't need to do that. So in order to do that, w.grad set 0, 0 in place. So this changes the gradient to 0. Then when we calculate again, it just happens naturally. Otherwise, if you don't do that, you will get a different result, wrong results. So now let's run this. Before running this, let me print few things. So let's copy this, paste it there. Looks good. So I'm going to run this now. So this is pretty good. Even after completing just four data, our loss is did I make? Okay, I think I made a few mistakes here. So the loss we need to change. I need to add a few things. L sum equal to 0. Then add the loss. Maybe I'm not going to do this because if we are adding this, it will change a few things. Maybe let's run this and see what happens. Okay. So it didn't. Maybe let me rerun. Okay, I think this looks good. Cool. So what happens here is instead of using gradient function, so if you see the previous section, we calculate the gradient ourselves, some 2x xw minus y. Let's say you don't know how to do this. You just use PyTorch way of doing this. W L dot backward and then w dot grad. So this has the same gradient that we calculate above. Then we can replace. Here we are doing gradient descent update. What happens initially is the loss is 13.02 something. Let's check the previous one. The same 13.025 and W is 1.41, and after that it became 0.622. Even here it becomes 1.41 to 0.622. So we replicated the exact same thing, but this time we didn't use our gradient function. We used PyTorch way of doing things. Good. So this is one thing. Maybe let's see if there is any questions. Good. So now what we are going to do is we are going to use completely PyTorch to solve this problem. So I'll be doing a few changes. One is let's use just PyTorch linear regression. Okay. So if we see our data, let's copy the data. Okay. So if you are using PyTorch to do linear regression, you need to do few changes. One is we cannot put all the data like this. We need to put all the data inside a list or something. So X data becomes torch.tensor. Then you put it inside a list. So it's like this. And it's a float. So to create a float, you just type 1 point something. 2 point, 3 point, then 4 point. Okay. So our X data is good. This is torch.tensor. And similarly for Y data, the same. PyTorch.tensor, then you type 0.621, then 1.242, then 1.864, then 2.485. Okay, so our X data, Y data is ready. Now we are going to create a model. We are going to create a linear regression model. So class maybe let's type model. So before that, we need to import a few things. Since we are using PyTorch neural network library, we need to type import torch.nn as nn. So this nn is neural network. This has so many functionalities. We'll be using those to create a model for us. Okay. Then you need to put nn.module as a superclass so that you don't need to create parameters by yourself. It will create automatically. Then def init, cool. So super.init, then self.linear, nn.linear. So in our case, this is just one input and one output. So you type 1, 1, and we are setting bias equal to false. Otherwise, we just need weights. We don't need bias. So if you need both, you can leave just remove bias equal to false. But for our problem, it's very simple. There is no bias. This is just multiplication of weight. So I'm just setting bias equal to false. I think that's pretty much that's it for init. Then you are creating forward function, def forward. In forward, what we do is you get some input data x, then you calculate the prediction y pred equal to self.linear, and you pass the data. That's it. Then you return the prediction. That's it. Cool. We created a model. Now let's instantiate the model. Model equal to model. Now if you pass model.forward, and let's say you want to know 50 kilometers. Okay, for 50 kilometers, it says minus 19 miles, which is totally wrong. Let's see why this is wrong, because model.parameters, you cannot access the model parameters just like this. You need to wrap this inside a list because it's a generated object. Okay, so our w equal to minus 0.38. So we know that when w equal to 0.62, the result will be perfect. Currently this is minus 0.38, which is completely wrong. Now let's build a model and see what happens. So we have created a model here. Now we need to do a few more things. One thing we need to do is we need to create a loss. In previous section, we created loss like this, like we created a function. But when you are using PyTorch, there are a few things to do that. We can just import from nn module. That's one thing. And then we need to create stochastic gradient descent. So currently we are doing stochastic gradient descent like this. So instead of doing this, we'll be using PyTorch Optim. So I'm going to introduce a few things. One is loss. In PyTorch, loss is called criterion. Let me type this. In PyTorch, loss is called criterion. So criterion equal to nn dot. We need to use mean square error loss. Okay, that's one thing. And optimizer, which is gradient descent. We can get optimizer from torch.optim.stochastic gradient descent, SGD. Then we need to set what parameters to pass. We can get that from model.parameters. Then we need to choose a learning rate, LR equal to 0.01. run this. Okay. So now what we can do is we can do training for epoch in range 10, y prediction equal to model of x data. We can pass all the data at once. Then we can calculate the loss equal to criterion of y prediction comma true label y data. Once loss is calculated, we need to backpropagate L loss dot backward. Then we need to do stochastic gradient descent update. We call this as stepping. Optimizer dot step. Then we have calculated the gradient. Once we calculate the gradient, we need to zero the gradient so that otherwise it will accumulate. So optimizer dot zero grad. Then pretty much that's it. Maybe after each epoch print loss. I'm going to type both epoch and loss. So I mean let's type loss, and then let's also, I think, loss is fine. Let's run this. Okay, so initially the loss is pretty high, 7.57. After free epoch the loss is 0.40. We can train longer. Maybe let's check the parameter and see what happens. Now I'm going to run this. So this is 0.42. We know that when 0.62, that's a good one. Maybe let's increase the learning rate and see what happens. Let me re-initialize. Okay, so I increase the learning rate. Now I'm going to run this. So this is pretty good. We are getting close to 0. Now list model parameters, and we are getting 0.6205. Maybe let's ask what happens if it's 50 kilometers, the same question. Okay. Model dot forward and torch dot tensor, and you can ask 50 kilometers. For 50 kilometers, it says 31.02, 31.06, which is pretty close. So in today's session, what we did is we expanded our previous session, which is understanding everything using NumPy. Here we did two things. One is we removed gradient by using torch gradient w.grad. This is one change. And then we implemented everything using PyTorch linear regression. For that, you need to do three things. One is you construct a class which is model. In model, you just tell how the model looks like, how many input and how many output, and you can also create many different layers one by one. So we will see those in our upcoming sessions, but for now this is like a simple model. And then you need to do forward. So this forward just takes an input and it knows how to calculate the output. So that's all you put here. Then you instantiate the model. After instantiate the model, you need to do a few things. One is constructing the loss criterion, and then you need to use some optimizer for gradient descent. Then these steps are simple ones. Then finally the model training happens. So whatever we learned today, the same concept applies for even huge models and huge data sets. The approach is very simple. Maybe next session we will try to do a few more complex challenges. Thanks everyone. See you all next week.